Okay, I'll tell you a little bit about flow control devices for the measurement of gas flows here in the laboratory. I'm standing in front of a panel that has a lot of piping behind it. It's a fairly typical flow control panel, at least here at the university, for controlling the flow rates and mixing rates of various gases. So this particular panel can control probably as many as 3 different gases. These 2 gauges would each control the flow of one gas, and they do it through what's called an orifice plate. And I'll come around to the back side of the panel and show you where that is, and we'll talk in class a bit about how it works. Let's for the moment focus on this device here. This is called a rotometer, and you can come in close and have a look at this. A rotometer is used for measuring the flow rates of gases, and typically it cannot handle very, very high flow rates. What you see here is a glass tube, and the tube is a Matheson tube. That's who manufactures it. And this one is a 605, and a 605 will handle a number of different gases, but air, nitrogen, and oxygen, I think, are typically flowed through this. The tube itself can handle 2 different ranges of flow rates, and those 2 ranges are represented by the 2 different balls that are inside the tube. One is steel, and one is a plastic or glass of some kind. So one is heavy and one is light. The tube itself is slightly tapered like this. So the gas comes in the bottom of this rotometer and lifts the ball up into the air. Gases flow around the outside of the ball, and the level of the ball has been calibrated for the flow rate. So you would turn this knob, and that would result in these balls going up the inside of the tube, and there would be a calibration sheet that told you what that value represented in terms of flow rate. It's the weekend here at the university, so none of the gases are on, and so I can't demonstrate this for you. Let me show you the orifice plate side of things. So we'll learn in class that an orifice plate allows you to flow a gas across a plate that has a hole in it, and the pressure drop across that hole is calibrated against the flow rate. And I'll show you the back side of this panel so you can get an idea of what it looks like. So here we go. Those are the 2 orifice plates, and inside those plates are inside those housings are plates with holes in them that are a certain known size, and it's a knife-edged orifice. In other words, a very sharp-edged orifice. And pressure is read between a static tap and one side of that orifice plate, and the pressure you can sort of see that right here. So you have a on one side here goes to our gauge. Let's see if you're, yeah, one side here goes to our gauge, and then this is the other side, okay? And the difference gives you the flow rate across that orifice. And there are 2 of them, both going to the back sides of those gauges there. Okay, and then a whole bunch of other piping that relates to how this thing mixes and flows gases. We have a bank of oxygen cylinders sort of hiding behind there, and house compressed air and nitrogen. One set of one of these outlets comes out there at the bottom, flows through this yellow pipe and into this box here, and this box is full of beads. Okay, so this section right here is full of a bunch of beads, and that's called a settling chamber. And then the air flows through this venturi, and the combination of these 2 elements straightens the air and gives you what's called a top hat profile as you go into this duct, which is the subject of some experiments that we're doing here in this lab. Okay, so that gives you a nice predictable inlet condition for the air to this duct. All right, let's look at a couple other things while we're talking about gases. So here's a pretty standard cylinder, okay? And what you see here is the top of the cylinder, and this is the main valve that controls the flow from the cylinder to this side of the regulator, And what we see right now is that there's about 1,000 psi in this tank. This is a tank of oxygen, okay? So when we open that up, this guy reads 1,000 psi. And then it goes through this rate. That's too high for most of your normal laboratory applications. So what we do is then go through this regulator, all right? And the regulator drops the pressure down to this value here, which it's currently reading 30 psi or so. Is that right? 10, 20 psi. 10, 20, 30. Yeah, 10, 20, 20 psi. Now the tricky part about these guys is that in order for this gauge to be accurate, the gas needs to be flowing, okay? So this valve controls the pressure here. And as you can see, when I turn that up, it's going to bump it up to 30 psi, okay? But it's not flowing right now. So it really needs to be flowing with all the resistance in place. And I currently just have it going to the atmosphere here, okay? So this is just oxygen that's going to be flowing out of here, and we'll double check, make sure. So it's all written on the outside of the tank. It says compressed oxygen. We don't want to be flowing something nasty into our laboratory. So we can open that guy up, and we hear it flowing. Now, you see the gauge reads 30 psi. However, if your line that you attach to this had some resistance in it, it would change the reading. See how that bumps up and down a little bit? So the reading will be somewhat dependent on the rest of your system. If that really slow, with no resistance, it drops down to about 25. If we block it, it jumps back up. Okay? You can decrease or increase that flow rate while it's flowing using this valve. Okay? All right, I think that's enough oxygen for now. I feel quite rejuvenated. All right? Good. And I'm going to turn this whole thing off and bleed it, and everything goes down to 0. Great. Okay, here is this is another assembly for measuring flow rates. You can see again, you have some gauges. This one's a little uglier, but these are your orifice plates right here. And in this particular assembly, what you're seeing is these screws control little Teflon plugs that go into holes in the orifice plate. So you can have one or more holes open, and then you would calibrate this thing for the number of holes that are open. And you can see these are all numbered 1, 2, 3, and 4. And down here someplace it's going to say that if you have number 2 open and the PSI reads 72, your that looks like a velocity coming out of there is 0.5 meters per second. So this is somebody's work a while ago. I would be looking for, let's see, centerline velocities. These are all centerline. Here's a flow rate over here. So this person has calibrated this thing and said, for a volume flow rate with the bottom right screw unscrewed, that would be this one, at 10 psi, you're going to get a flow rate of this many cubic meters per second. So you would set this gauge to 10, and that would give you this flow rate. And then they've calibrated all the way up. And then they have both bottom unscrewed. And what we should see at 10 psi is a higher flow rate, which indeed we do. Okay? While we're here, let me show you this big gizmo. This is called a bellows. Okay? And I'll hand off my camera again. This is called a bellows. And a bellows is kind of an old school device for measuring volume flow rates, and this is pretty old. I'd say 100 years or so. Let's see, actually, does it say? Well, it says 1258, but I think that's a serial number. I don't think it's that old. So what you do is you fill this thing with water and then attach a hose to it, and the hose fills an interior chamber with gas, and the rate at which this thing rises tells you the flow rate of gas that you have going into the chamber. And I actually have used this quite a lot in my experimental work because they're quite good for getting smaller flow rates of gases. Okay, one more thing to show you. over this way. So we'll talk a little bit about velocity measurements as well. We're going to look at a hot wire anemometer and a Venturi and a pitot static tube, things like that. But one of the more advanced ways to look at velocity flows is with this particle image velocimetry system. And what you have here is a CCD camera and a laser, and the laser acts like a flashbulb. And what it's doing is illuminating a sheet of laser light. It's basically producing a sheet of laser light in this chamber, and this particular chamber is being used to do some plume experiments. And we need to seed the flow with little particles, and we seed the flow with an incredibly sophisticated Haunted Mansion fog machine for $30 from your local Halloween store. Okay? So that's how we seed the flow, and I'll get that going, I hope. There we go. So we're going to fill that up with some smoky stuff, and then I'm going to put on my goggles so that I don't get laser light in the old eyes, and I'll crank up my laser power, and you can just keep focusing on that over there. And when we do that, what you can see, I hope, yeah, you can see that. What you can see, if you come on over this way, particularly outside the chamber, is some of the flows that are generated as a result of seeding this flow, and the camera will take pictures sequentially of all of those particles, and use software to stitch together the path that they're traveling. And when we look at the output from the software's calculation of those trajectories, if we look over here, let's see if you can get an image of that screen. Yeah, that looks pretty good. You get a whole bunch of arrows, and the arrows show you which way the gases are going, and what you see is essentially we've created a plume using a candle in this scaled model. So, and those arrows are all indicating the direction of flow around that plume. And I don't know if it gets any more interesting than this with some other pictures, but that's about the gist of it. Okay.